Every time you get a movie recommendation or see one of those incredible AI-generated images, you're really just seeing the very end of a long, complicated process. But what if I told you that hiding underneath all that modern wizardry is a single, almost ancient mathematical trick? Well, today, we're going to pull back the curtain on the fundamental engine that makes all of it possible.
So, what is this hidden engine, really? What's the one computational pattern that just shows up everywhere, from training massive models to predicting the next word in a sentence? It's something so foundational that, honestly, it's pretty easy to miss entirely.
And the answer is solving systems of linear equations. And we're not talking about a few, we're talking about billions of them at a time. See, every time an AI model trains, what it's really doing is trying to find the perfect settings, the perfect parameters to get its errors as low as possible. And that whole search for perfect is framed as one giant problem of solving a massive linear system. This is the quiet, relentless workhorse of modern AI.
So in this explainer, we're going to follow the story of how we got so good at solving these problems at scale. We'll start with the problem itself, then we'll get into the first really brilliant systematic solution. From there, we'll see how that was refined for pure elegance and then totally rebuilt for raw speed. And finally, we'll talk about how you choose the right tool for the job.
Okay, so what does it actually mean to solve a system of linear equations? I think the best way to wrap your head around it is to picture it geometrically. Imagine each one of those equations is just a flat plane, kind of floating in space.
The solution, then, is that one single, precise point in space where every single one of those planes crosses. It's the unique set of values that makes every equation true all at the same time. Finding that one exact point, well, that's the whole game.
All right, so our first big tool for finding that intersection point is called Gaussian elimination. The best way to think about it is like refactoring your code. You're moving things around, you're changing the structure to make it way cleaner and easier to read, but you're not actually changing what the code does. The final output is exactly the same.
To do this refactoring, we've got a toolkit of 3 simple but really powerful moves. They're called elementary row operations. We can swap any 2 equations, we can multiply an entire equation by some number, or we can add a multiple of one equation to another one. And that's it. Those are the only rules, but they give us everything we need to simplify the whole system without ever losing track of that final answer.
The whole process is called forward elimination, and it's just beautifully systematic. You use those row operations to surgically remove the first variable from every single equation except the top one. Then you just move to the next column, do the exact same thing for the second variable, and you just keep repeating this, moving down and across, until the system forms this really distinct staircase shape.
Now, this staircase structure actually has a formal name. It's called Row Echelon Form. Each of those leading non-zero numbers you see is called a pivot, and they kind of act like anchors for our solution. Getting to this staircase shape means we've successfully started to isolate our variables, which makes the whole thing much, much easier to solve.
So once we have our nice staircase, the solution is right around the corner. You start at the very bottom equation, it's the simplest one now, and you solve for its one variable. Then you take that answer, plug it into the equation right above it, solve for the next variable, and you just keep working your way back up to the top. It's this clean 2-step dance: forward elimination to go down, back substitution to come back up.
But what if we could get the answer even more directly, without that final climb back up? Well, that brings us to our next method, Gauss-Jordan elimination. You can think of this as the perfectionist's approach. It just extends the process a little bit to create an even cleaner, more elegant final form.
See, the goal here isn't just a staircase. The goal is to get to something called reduced row echelon form, and this is a very strict structure. Not only do you get rid of the variables below each pivot, but you keep going and eliminate them from above each pivot too. And for the final touch, you scale every row so that every single pivot is the number 1.
The absolute beauty of this is that once you get to reduced row echelon form, you're done. The work is finished. There's no back substitution, nothing. The system has basically solved itself, and the answer for each variable is just sitting right there, plain as day, in that final column.
Okay, but all that perfection comes at a price, a computational cost. And for engineers who are really focused on performance and scale, especially in AI, there's a different way to think about this that prioritizes speed, especially for repetitive tasks. And that brings us to LU factorization.
So here's the crucial engineering problem you run into. Gaussian elimination is awesome if you're just solving something once. But what if you have to solve the same core system, the A in AX equals B,
over and over again, but for thousands of different output vectors. Well, redoing that entire elimination process every single time would be incredibly wasteful.
And this is exactly where LU factorization shines. Honestly, the best way to understand it is with an engineering analogy. It's basically a form of pre-processing or caching. You do all the expensive, heavy lifting computation once, right up front. And after that, solving for any new output becomes incredibly fast.
So the strategy is to split the hard work from the easy work. We take our original matrix A and we decompose it into two simpler matrices, L and U. Now, U is the same upper triangular matrix we already got from Gaussian elimination. That's our hard work. And L is the special lower triangular matrix that perfectly stores a record of exactly how we did that elimination. By saving these two matrices, we can solve for any new output with two super fast steps. It is just orders of magnitude more efficient.
Okay, so we've got these really powerful tools, but how do we choose between them? Well, it all comes down to a classic trade-off, really. You're choosing between computational thrift and conceptual elegance.
I like to think of Gaussian elimination as the nimble architect. It does just enough work to build the scaffolding you need to get to the solution. It's the go-to for single-solve problems because it's just computationally cheaper. Gauss-Jordan, on the other hand, is the perfectionist. It does more work, for sure, but the result is this explicit, immediately obvious solution. And that's incredibly valuable for really understanding what's going on and for certain tasks like finding a matrix inverse.
So why does any of this matter? Well, because when you actually understand these foundational trade-offs, you get to peek behind the curtain of all those AI libraries and tools that we all use. You start to see past the simple function calls and begin to appreciate the rigorous, logical choreography that truly makes digital intelligence possible.
Ultimately, the methods we've talked about today, this is the bedrock. And it kind of leaves us with a final thought. As the tools of AI get more and more advanced, more abstract, are we making sure we're building on a foundation that we truly, deeply understand?